So our last speaker for today is Tian. She comes from the Nordic Institute for Theoretical Physics, and I heard she's moving soon, in 2 months, I believe, to Dresden for a new postdoc. But I also believe she's going to tell us a little bit more about herself. And she's going to also tell us about more than positive edge weights, structural balance, and random walks.
Thanks for the introduction. And also I would like to thank the organizers for organizing these nice events and also for having me here. And I have been enjoying the event so far and learned a lot. So hi everyone, my name is Tian. Currently I'm a research fellow at NORDITA, or Nordic Institute for Theoretical Physics. And it's in Stockholm now. So, and it's hosted by KTH and Stockholm University as shown there. I really appreciate this opportunity to present my research, which could be related to some higher order interactions, but not as far as hypergraph yet. I would happy to extend it for hypergraphs. So always happy to chat if you have any ideas. Specifically, I will talk about extending the network size toolbox for more than just positive edge weights, but also with negative values and complex valued weights to explain the relationship so as to consider more phenomena in our real life. As a junior researcher, I take it as a chance to introduce myself to you. So here is an introduction of myself. I grew up in a city called Zhengzhou in China, the same as Xue, actually. And then I went to Beijing for my undergraduate study in math, and then Manchester also for undergraduate in math. Then I did my PhD in Oxford, also in math, under supervision of Professor Nolan Biot. During this time, my PhD was in collaboration with industry, so Tesco here, the UK's largest supermarket chain. So during this time, I had regular meetings with my industrial collaborators to understand the real problem they would like to solve. And then with my academic advisor, we have proposed some network-based methods to first infer the relationship between products, including complements and substitutes, and then provide some solution for their decision-making problems, such as to maximize the sales or revenue, stuff like that. And during this period, I become really interested in these type of networks where we have positive and negative edges, because, for example, here we have these complements and substitute relationship between the products here. Then I moved to a postdoc in NORDITA to further investigate this problem. And that will be my talk mostly about. Yeah. Then why should we care about these positive negative relationship and also negative or complex valued weights? So we know networks can model a lot of systems. We can consider like social system. Then we can have friends and enemy, that's positive and negative. And we can also consider the human brain, where each neuron can be considered as a node. And if two neurons interact, we can put an edge here. And then it's natural to consider both positive and negative couplings, because the relationship can be excitatory or inhibitory here. And then if we consider some quantum systems, it's very natural we will encounter some complex values. So we can also extend the results for complex valued weights here. So the theme of my research is really to consider one of the classic problems in network science. So we look at the network structure, and we would like to see how it can characterize the dynamics on networks, but not only with positive weights, and we can have some negative edge weights, and also complex valued weights here. Specifically, we will first look at negative weights, which could be considered as a special case of complex valued weights, because if we restrict the angle to be 0 pi, then this complex value will be essentially positive and negative. And then we will extend the results for complex valued weights. So that will be the idea of my research and also my talk here. Specifically, I will talk about the structural properties via the notion of structural balance. and the dynamical properties via random walks here. And let's start with signed networks. We can consider some like typical dynamics on signed networks. Here I show a very simple opinion dynamics. Here, where each node represents a person, and then they can have different opinions on these problems. Should we vote for someone in the presidential election? And they can choose to say yes or no. And then they are connected by these positive and negative relationships, which represent their trust and distrust relationship. So for example, for these dynamics, at some point, one of them is convinced that, yes, we should vote for this one. And then at next step, it has some probability to meet its neighbors. And then if there's a positive relationship, then this one will be convinced that, yes, we should vote for this one. If there's a distrust relationship, it will be pushed to the opposite that, no, we won't vote for this one. So these dynamics can continue like that. And there are different ways to summarize these dynamics. One of them is to consider the state value as a probability to say yes minus the probability to say no. And then we can write the updating function as shown here, where xt is equal to what we call the signed transition matrix P here times xt minus 1. And the signed transition matrix P can be obtained by the degree matrix inverse times the signed weight matrix W here. And W is like the weight matrix encode the pairwise relationship between the nodes, and it can be negative. And we still define the degree of nodes as sum of the absolute values here. So that's positive. We can see this dynamics is largely dependent on the properties of the signed transition matrix or the signed weight matrix. So we will characterize these matrices so as to understand the behavior of what we call signed random walk here. Yes. Let's start from the classic notion of signed graphs, and that's what we call structural balance. It is motivated by the following ideas in psychology, where a friend of a friend is friend, an enemy of a friend is an enemy, and more importantly, an enemy of an enemy is a friend. Mathematically, this can be characterized as all cycles in the graph have an even number of negative edges. Then Hari has shown in his papers that this notion can be equivalently defined as a graph where we can find a bipartition with positive edges inside and negative edges between the two parts. And this motivates us to think of the opposite of this notion, where we can find a bipartition, but negative edges inside, positive edges between the two. And that actually gave us the notion of structural anti-balance, which can be defined as all cycles in the graph have an even number of positive edges. We essentially exchange the role of positive and negative edges. Actually, Hari has also shown in his later papers that this notion can be characterized by a bipartition with negative edges inside and positive edges between the two. So these two notions provide the basis of the classification of signed networks we would like to consider. And to complete the story, we group all the remaining signed networks to be strictly unbalanced. So it's neither balanced nor anti-balanced. And our idea is that we would like to consider very general signed networks characterized by this weight matrix W here. And we want to connect it with the one where we ignore the sign. So everything is positive or zero for sure. And then we can connect with the results we already have in network science and also non-negative matrices. That's the idea. And then we start from the spectral properties of the weight matrix. We start from these two special cases by considering the unitary decomposition of the weight matrix W and also W bar where W is equal to U lambda U transpose. U contains the eigenvectors. Lambda has eigenvalues on its diagonal. And same for W bar equal to U bar lambda bar U bar transpose. For the first type of structural balance, we can show that the eigenvalues are the same for these two matrices, and eigenvectors are connected by this I1 matrix, which is diagonal, and its II element is 1 if the corresponding node is in one of the node subsets, and is -1 if it is in the other node subset here. So that's for the balanced case. And then for the anti-balanced case, what we can show is that the eigenvalues are the opposite, and the eigenvectors are connected by these I1 matrix here. And it's another one corresponding to the anti-balanced structure where we have negative edges inside and positive edges outside for the bipartition. It is actually not hard to prove after realizing that the W is similar to W bar with this I1 matrix in the balanced case, and W is similar to the minus of W bar in the anti-balanced case. So that's like two very neat case. And previously we have grouped all the remaining sign networks to be strictly unbalanced, which potentially have a lot more sign networks than these two cases. And we also want to show some common properties of these type. And actually we found something. Specifically, what we find is that a sign network is strictly unbalanced, and that's an if and only if condition that the spectral radius becomes smaller, which is the largest absolute eigenvalue. And to show it, one direction is straightforward from what we have shown before, because if it's balanced or anti-balanced, it should have the same spectral radius. For the opposite direction, that all the strictly unbalanced sign networks have this property, we first show that we can, in these type of sign networks, we can find two walks of the same length, but of different signs, which means there are conflicts in the graph. And then we further use these results to contract the spectral radius of the sign networks by the definition of matrix 2 norm. And we know that the ij element of W to the power of k sums over all the walks between the corresponding nodes. So that's the key idea. So that would be the structural properties I would like to show here. And then we would like to apply that to understand more of the signed random walks we have seen at the very beginning. Yes, so for the first type of structural balance, we can show that the sign transition matrix, let's just recall that is D inverse times the weight matrix W here, has eigenvalue 1, that's the only case. There are many ways to show it. One way is to consider the previous results, but we assume an undirected sign networks here, so we require the corresponding weight matrix to be symmetric. And then, but we know that the transition matrix is similar to a symmetrically normalized matrix, so we can still apply the results we have shown before to get the results here. And then by considering a leading eigenvector, we can show that if the graph is balanced and is not bipartite, we can get to steady state of the signed random walk as shown in the X star here. So we see the effect of, can you see it? Okay. So we can see the effect of adding signs to the network is in the first brackets, because if we remove it, we retrieve the result, classic results of random walks on networks, where dj is the degree of the nodes, and 2m is the sum of the degree of all nodes. So now with signs, they can have different signs in these two parts. And it also depends on the initial state x0 and how it spreads over the bipartition through this I1 matrix here. One is just O1 vector. So that's for the balanced case. We have also discussed this anti-balance case before. So this is a bipartition with negative edges inside, positive edges between the two. We can show that the sign transition matrix has eigenvalue -1. That's the only case, following a very similar idea to the previous one. And then by considering a leading eigenvector, we can show that if the graph is anti-balanced and is not bipartite, then we have two different limits for the odd and even time steps, denoted by x star O and x star E here. And if we look at x star E, it actually of the same format as the x star we have shown previously in the balanced case. But now the I1 matrix corresponds to the anti-balanced bipartition. So it's negative edges inside, positive edges between the two. And then the one of odd time steps is the opposite to the one of the even time steps. So an extra effect of adding signs to the graph is that now it has this alternating behavior asymptotically. That's for these two special cases. And then for the very third type, from our previous results, we can show that actually the spectral radius of the sign transition matrix also becomes smaller than 1. Following very similar idea. And then we can actually have a steady state in this type, and that's 0. And how to understand 0, this steady state, if we remind of ourselves, we can consider it as a very simple opinion dynamics, and x can be considered as a probability of saying yes versus no. It means this difference between these two probabilities 0 asymptotically. So on average, they have neutral opinion. Because there are so many sign networks in this type, we also consider some measures to quantify its transient behavior. And we define some dissimilarity from being balanced through how far the largest eigenvalue of the sign transition matrix from being 1, and also the dissimilarity from being anti-balanced as how far the smallest eigenvalue is from being -1. And also, if the graph is not far from being balanced or anti-balanced, we can show that these measures are proportional to how many edges disturbing the balance or anti-balance structure by perturbation analysis. And that's the dynamical properties I would like to show here. And then I would like to show some numerical experiments to verify the results we have got here. Specifically, we consider 4 different sign networks and constructed in a way close to stochastic block model, but with signs. Specifically, there are 16 nodes in the graph, where the first 6 node is the first block, and the other 10 is the other block. And then we randomly place edges inside and between the 2 blocks. For the structural balance configuration, we only allow positive edges inside, shown in black here, and negative edges between the 2, showing orange here. And then for the strictly unbalanced one that is close to being balanced, we randomly flip a few edges. And then for the structural anti-balance structure, we only allow negative edges inside, orange, and positive edges between the 2, in black here. And for the strictly unbalanced one that is close to being anti-balance, we randomly flip a few edges again. And then with the initial state, we can see the evolution of the sign random walks and to explore different behaviors of different sign networks. And it's shown here, where the x-axis corresponding to different nodes and the 4 different panels corresponding to the 4 different sign networks we have shown before. So, and the y-axis corresponding to the state value, and different colors correspond to different time. And the blue one is the initial state. And then we have the orange one for t is equal to 5, and then 10, 15, 20. So we also have this odd and even time pattern here. Then for the balance case, we can see that it have the same sign, keep the same sign over time, and it approaches specific values over time. And for the strictly unbalanced one that is close to being balanced, it has a similar behavior in terms of the the keep of the sign and also the overall shape, but it approaches 0 over time. And then for the structural anti-balanced case, we can see that it has like a different sign in odd and even time steps. It also approach different limits in odd and even time steps. And then for the strictly unbalanced case that is close to being anti-balance, it has a similar behavior in terms of the overall shape, the sign change, but it approaches 0 over time. So this really verifies the results we have shown before. And yes. Cool. And before I move along, I would like to do a working summary here. And up to now, I have introduced a classification based on structural balance for sign networks, and then characterize the spectral properties in each type. And then we have applied it to analyze the random walks on sign networks. And one argument I would like to make here is that even though I only showed the results for random walks, the results also hold for other dynamics that are largely dependent on the weight matrix. For example, we can just replace the sign transition matrix by the sign weight matrix, and we get a very similar behavior. And we can also have some nonlinear effect, like the threshold effect. Results also hold to some extent. And for future directions, we can consider like some more applications because the signed random walk is a bit simple at the moment, and we can add more effects from the real world so as to consider more application here. And hypergraph could also be very interesting in this setting. Last but not least, actually these balance and anti-balance only compose like 2 switching equivalent classes on sign graphs. Because we can consider the side and then switch the sign of the edges between these sides is complements. That's what we mean by switching on sign graphs here. So it will be interesting to consider more switching equivalent classes so as to provide finer characteristics of sign networks. The work I have talked about today in this part is mostly based on these article here, so feel free to check it if you are interested. Also, if you have any questions, I can answer here or I will move on. Okay. So up to now, we have seen the results between the structure and dynamics on sign graphs. And now I would like to extend it for complex valued weights. And just to make it clear, we consider this Hermitian case. And for all the other cases, we consider it as very interesting future direction to explore. Yes, please. No worries.
Why are you maintaining the sign graph as your thing? Would it be equivalent to take the cover graph or to the signing and then you have a random walk on a regular graph? I mean, not regular, but like a normal unsigned graph.
What do you mean by cover?
Like for every sign graph, you have like the
Why?
cover that's associated with it, where you replace every vertex with 2 vertices, and then if you have a negative edge, you join them with an X, and if you have a positive edge, you join them with an equal sign. So that this
the sign random walk should be equivalent, and you retrieve the probabilistic explanation on the regular graph. Yes. Yeah.
So you actually prove results about this type of random walk, and you're maintaining the sign graph version. Is there a reason?
I think that's our probabilistic explanation for these type of sign random walks, but there can also be other type of signed dynamics. We just use it to show that our results hold, if I answer your question, or we can discuss later after the talk.
So that's easier because you have much more. But you have a constant number more. Twice. What? Twice same order of language.
It actually has a name. It's like Graham expansion of graphs. Mhm.
How many switching classes can there maximally be?
I think it depends on the nodes you have. Because for example, for nodes of three nodes is very simple. Clearly you have these, yeah, three. Mhm.
Which quantities can you bounce them off switching classes?
I guess it's the nodes, but I'm not sure. The number of nodes you have. Yeah. Yeah. Yes.
Is there agreed upon notion of a cycle and a hypergraph? All right, no, that's not what you're talking about. No, the accepted from perspective. I would think that there are many other. Yeah.
Okay. Good. Thanks so much. Should I move on or cool? Yeah. So we will look at complex valued weights, and I would like to start with these dynamics we have considered before. But now with complex values, we can consider a whole spectrum of opinions, characterizing by this angle from saying yes. And then the relationship between the nodes can also be like characterized by complex values. For example, the relationship between these two nodes in the middle is not just trust or distrust, but mostly trust, characterizing by the theta of pi over 3 in one direction, and then phi pi over 3 in the opposite direction, just to make the information flow consistent in both directions. And now for the dynamics, if this node meets a neighbor in the middle, in the next time step, if you be closer to say yes, but not exactly, and characterizing by these theta equal to pi over 3 here. And these dynamics can continue like that. There are, again, many ways to summarize these dynamics. If we consider it as the characterizing by this theta as a complex value, and then we multiply it by the probability and we sum them together, and then we can write the updating function in a very similar format as we have seen in the classic case. So xt is equal to p times xt minus 1 here, and we call this p complex transition matrix, which can be obtained by d inverse times w. And W is now the complex weight matrix. So it encodes a relationship between the nodes and can be complex. And the degree, we define it as the sum of the modulus of the edges that are incident on this node. And we call it complex random walk here. And we will, so we see again, it's the behavior of these random walks is largely dependent on the complex transition matrix or the complex weight matrix. So we will characterize them so as to characterize these complex random walks or dynamics on complex weighting networks. We again start from the notion of structural balance, but now we can have different faces, or what we call faces, or the angles of edges in the network. So we first define the face of cycles as the sum of the faces of the composing edges, and then we modular 2 pi. So it's between 0 and 2 pi. And we define the notion of structural balance as all cycles in the graph has phase 0. And then we can show a similar structural theorem where this notion can be effectively defined as we can find the partition of the graph, and then inside the partition, edges have phase 0, and between the same pair of node, like the node subset, they have the same phase in the same direction. And if we consider each node subset as a supernode, and there's any cycle of these supernodes, this cycle will have phase 0. Here I show an example of 3 blocks here. And then we also consider the opposite notion, what we call structural anti-balance. And we define as all cycles in the graph after adding pi to each composing edges have phase 0. And then we show the corresponding structural theorem for balance as well, where this notion can be effectively defined through a partition of the graph, where inside the node subside, edges have phase pi, and between the same pair of node subsides, they have the same phase. And if we consider each node subside as a supernode, and there's any cycle, after adding pi to each composing edges, this cycle has phase 0 here. So here is an example of 3 node subsides. These two notions again provide the basis of the classification we would like to consider to complete the story group of the remaining complex weighting network to be strictly unbalanced as before. So the idea is very similar to the previous case. We consider very general complex weighting networks where the edge weights can be complex, and we would like to connect it with the one where we ignore the phase information, we only consider the modular of the relationship. And then we can connect with the results in classic network science and also non-negative matrices here.
Would be a notion of switching in this case?
That's a good question. I think because we don't really consider switching here, and if we, I think with the different phases in the graph, we can define different switchings. Now probably it's like a function of theta now. It's like still 2. Maybe you need more no subset to do that, I think. Yeah. I will consider more after the talk. Yes, so I will start from the spectral properties of these two special cases. Again, by considering the unitary decomposition of the complex weight matrix W, and the one where we ignore the phase information, what we call W bar here. And the results looks very similar to the previous case. Specifically for the balanced one, we can show that the eigenvalues are the same and the eigenvectors are connected by another I1 matrix, depending on the partition we can get from the complex weighting networks. So now it's still diagonal, and then the I element encodes the phase of the path from node subset V1 to the node subset the nodes belong to. For example, we consider it as V1, that's V2, and corresponding to it, the phase should be 2 pi over 3, and that's in this complex value here. So that's for the balanced case. And then for the anti-balanced case, we can show that the eigenvalues are the opposite and the eigenvectors are connected by I1 matrix but corresponding to the anti-balanced structure we have discussed before. Again, this also based on the realizing that the W is equal to is similar to W bar with respect to I1 matrix in the balanced case, and W is similar to the opposite of W bar in the anti-balanced case. Yes, and then for the strictly unbalanced complex weighted networks, we have grouped a lot of complex weighted networks here. And again, we can show some common properties of this type. Specifically, we can show that a network complex weighted is strictly unbalanced if and only if the spectral radius becomes smaller after adding the phase to the weight matrix. The proof idea is also very similar, where one direction is simple, and for the opposite direction, we can show that we can find a walk between the same pair of nodes, but they have of the same length, but they have different phase, which means there are conflicts in the graph, and then for the user to contract the spectral radius of the weight matrix, complex weight matrix W here. And then we can apply these results to characterize the complex random walks we have seen before. And in a nutshell, what we can show is that for the first case of structural balance, the complex transition matrix has eigenvalue 1. That's the only case. And if the graph is not bipartite, we can get a steady state of these complex random walks. Now it can have different phases in different blocks corresponding to the balance structure. And then for the anti-balance case, we can show that the complex transition matrix has eigenvalue -1. And if the graph is not bipartite, by considering the leading eigenvector, we can get to limit for odd and even time steps, where the even one is of the same format as the previous X star, but the I1 matrix corresponding to the anti-balance structure, and the one for the odd time step is the opposite. And for the very third type of strictly unbalanced, we can show that the spectral radius is smaller than 1. And then we have a steady state of O0 in the network. Okay, time for a summary of this part of the talk. So up to now, I have again introduced the bipartition based on structural balance and also characterized the spectral properties in each type. And then we have applied it to analyze the random walks or complex random walks, show the different behaviors in different type. Actually, we have also considered some applications, for example, spectral clustering based on complex weighted networks, and also provide further characteristics for magnetic Laplacians. And if you are interested, feel free to check our article online. And I hope it's clear of these, the idea of this line of research. So from positive weights to negative ones, and then to complex valued ones. And if you have any ideas or comments or questions, please feel free to contact me. That's it. Thanks so much.
Any questions?
Did you look into the literature of voltage graphs when you did this?
Voltage graphs.
Yeah, so they
Is-
are graphs where you have on like your complex weighted value, you have weights that are roots of unity, and they're used to specify embeddings in orientable surfaces.
Ah,
And
I
they
see.
also have a full spectral theorem and a switching.
Oh, I should read more. Yeah, definitely.
And also there, I think it's called an unramified cycle or ramified cycle, like you're balanced and
Ah, I see.
And also,
Cool. Thanks so much.
Is there any other questions, suggestions?
Yep.
Why don't you consider edge weights in any field in Epson?
Because we want to start with something simple, so I can do. Oh, oh, I see. Because
but they're
Uh,
essentially doing that.
doing
by
the-
restricting the weights to a certain roots of unity.
Sure,
With a
sure.
character group.
In the balance, anti-balance case,
Yes.
she's doing that. But in order to have a more natural notion of the other unbalanced case, probably take it in a finite takes values in a finite cyclic field or so, and then have only
Yes.
finite in many situations.
Yes. That is what they do for voltage graphs.
Okay.
I think we consider it as a special case in some section of our papers where we consider the cyclic case. It's like the phase can only be 2 pi over k. And then we have some good, like, we can also interpret it as a layer thing. We were discussing about the sign networks stuff. Yeah.
Is there any other question? So I actually have a question. So I see some relationship with the canonical constant via these transition probability metrics.
Mhm.
If you don't normalize, but okay. Do you know if this complex random walks also could play a role as a graph invariant? Or if it has been considered?
I'm not sure. Maybe I should know more about the thing you were talking about.
Or maybe something to discuss.
Yeah, yeah.
Is there some other question, comment, suggestion? Okay, yeah, one more.
Yeah.
You started saying that you work with data from textbook.
Yes.
I was wondering I see there in the Tesco cafe. Is there any application there that you?
I think for the signed one, definitely yes, because we extract the relationship between products from the data they have, and then we can construct a network that has connected by positive and negative edges. So definitely we can construct the sign networks. I think we have already done it in my thesis. So that's something we have done. And for the complex weights, I think we can tune it to like not just positive and negative and how positive or how negative it is. And then we can construct a network with complex weights. And then with these networks, we have considered like the decision-making problem I have discussed before, but our dynamics is very simple, it's very linear. It's like the sales of these products will change like this portion of sales of other products. And we can make some decision based on these simple dynamics. But I believe this will need to be incorporated into more complex algorithms they have. Yeah, thanks.
Okay, then if not, let's thank you again.
Thanks.